This is Chapter 10, Magnetically Coupled Networks, Sections 1 to 2. Our learning goals for these sections are to consider mutual inductance, or the behavior of inductors sharing a common magnetic field, and also energy analysis, the relationship between mutual reluctance and self-inductance. Section 1, Mutual Inductance. If a current I flows through n turns of wire, forming a coil, it will develop a voltage V across it and also a magnetic field phi. Lambda is equal to n, the number of turns, times phi. And lambda is the total magnetic flux linked by the n-turn coil. Lambda is also equal to Li, which is Ampere's law, assuming a linear representation of the inductor. In addition, the voltage across this n-turn coil of wire, V, is d lambda dt, which is Faraday's induction law. Bringing these two concepts together, we get the familiar relationship for the voltage across the inductor in the time domain. V of t is equal to L di dt for an ideal inductor. This assumes a constant L and obviously a linear model. For mutual inductance, we have two coupled coils. That's the mutual part. We have a current I1 flowing through a N1 turn of coil, developing a magnetic flux, and the magnetic flux links the second coil, which has N2 turns. The total flux linkage, lambda, is equal to N phi, and the units of that are Weber. If a linkage is created by a current flowing through the coil, lambda is equal to Li for Ampere's law. The voltage created at the terminals of the component, as we just saw, are V is equal to L di dt, which is Faraday's induction law. Bringing those two concepts together, we can come with the realization that there's a voltage induced in the second coil, and we'll call that V2, and that would be d lambda 2 dt, or if you will, d by dt of N2 phi. Substitution what phi is equal to, we would get d by dt, the quantity of N2 times the quantity L1 over N1 I1, and multiplying through and straightening out the derivative, we would get the ratio of N2 over N1, L1, because they're all constants, and the only time-varying property subjected to the derivative would be di1 of t dt. And in fact, the term N2 L1 over N1 we'll call L21. In this case, we have another situation where we have not only the current I1 flowing through the first coil with N1 terms, but also a current N2 flowing through the second coil with N2 terms. They would develop voltages V1 and also V2. V1 would be d lambda 1 dt, or L1 di1 dt plus L12, the mutual inductance, di2 dt. And likewise, V2 would be d lambda 2 dt, which would be L21 di1 dt plus L2 di2 dt. Lambda 1 is equal to L1 I1 plus L12 I2, and lambda 2 is equal to L21 I1 plus L2 I2. The use of the terms L12 and L21 represent mutual inductance, and often they are equal to one another. L1, the I1 dt, is due to what we call self-inductance, also L2, the I2 dt, and would appear whether there was any coupling at all. And the mutual inductance terms, L12 di 2 dt and L21 di 1 dt, represent the coupling. L12 generally, as we said, is equal to L21, and we'll give it the symbol M. We'll assume that this is a linear model and that the two quantities are in fact equal. Here we have two coupled coils with different winding configurations. We'll take L1 is equal to the first inductor, which has N1 terms, and L2 is the second coil with N2 terms, if you will. We end up with lambda 1 is equal to L1 I1 minus M I2, which is the contribution of the secondary current on the first coil. And also lambda 2 is equal to minus M I1 plus L2 I2. Again, the contribution of the first coil on the second coil. We can then formulate that V1 would be d lambda 1 dt, or L1 di1 dt minus M di2 dt. Likewise, V2 would be d lambda 2 dt, or minus M di1 dt plus L2 di2 dt. We used a notation common in electrical engineering, the dot notation, to refer for the polarity of the induced fluxes. So in the case that we have here in the middle panel, we see that the induced currents flowing through L1 and L2, the dot notation indicates the direction of the way the winding is made. The windings are made basically in the same direction. Whereas in the bottom panel, the dots indicate that the voltages induced are in fact opposite to one another. That's because the windings are in opposite. So for example, one would be clockwise, the other one would be counterclockwise. So that's our circuit then for these mutual couplings and the resulting voltages. Notice that when the dots appear at the same location, the secondary voltage becomes M di1 dt plus L2 di2 dt. Whereas if the dots are in opposite directions, notice that the term has a minus M in it. That's the only difference between those two representations. And that's because of the polarity indicated by the dots. If we have N circuits interacting, then we could have a variety of total flux linking the circuits, which we can analyze. And we would do that by doing the flux linkage one part at a time. So for example, lambda sub ij would be the flux linking circuit I caused by the current in circuit J. This is because we have more than one circuit being linked. For linear inductor models then, lambda ij would be L sub ij times ij, and L sub ii would be the self-inductance of the ith circuit, and L sub ij would be equal to M L sub ji, or the mutual inductance between the circuits I and j. For n equals 2, which is a special case, lambda 1 would be L11 I1 plus L12 I2, and lambda 2 would be L21 I1 plus L22 I2. And of course, we assume a linear model, so L12 is equal to L21, the mutual inductances. Here we have a learning example considering the dot convention review. We have two coupled coils, L1 and L2, whose mutual inductance M, and the dot notation is as shown. The voltage V1 drives a current I1, and a voltage V2 drives a current I2. The current and voltages then follow the conventional passive sign convention. Flux 2 induced at voltage then has a positive effect at the so-called dot notation. V1 is then equal to L1 di1 dt plus M di2 dt, and V2 is M di1 dt plus L2 di2 dt. For other cases, we have to change the polarity or the current directions to convert to this fundamental case. As shown now, the dot convention has been changed so that the two dots are at the bottom of the inductors as far as their mutual coupling is concerned. We then have, as a result, minus I1 of t flowing, and also minus I2 of t flowing. That induces a voltage in the secondary circuit of minus V2 of t, or V1 of t is equal to L1 minus the I1 dt plus m minus the I2 dt. And minus V2 then is m, the same m, but minus the I1 dt plus L2 minus the I2 dt. So notice the change in the polarity that results from the initial case to the secondary case with the change in the dot notation. We can collapse the equation and write it in a more compact form if you want. V1 is equal to minus L1 di1 dt minus m di2 dt, and V2 is m di1 dt plus L2 di2 dt. Please note that there is no concept of minus L1. It's just that there was a minus sign associated for V1 from I1 of t. Now we want to write the mesh equations for this circuit with the assigned mesh currents. Notice the configuration of the coupled coils. It's not exactly what we expected because there is no separation between the first and secondary circuit. They seem to be part of the same mesh network. We have a voltage V1 of t through a resistor R1, an inductor L1, and an inductor L2. Notice the dot notation for the mutual inductance. We'll call a mesh current I1 of t then flowing in the first mesh, and in the secondary mesh consisting of L2 and R2, we have a current I2. So we're going to basically write mesh equations, but recognizing the effect of the mutual inductance also. So for example, the mutual inductance that would appear would be a function of the coupling between L1 and L2. So we'd have m di1 dt, and we'd also have coupling which would be due to the difference in the current, I1 minus I2. One coupling is due to I1 flowing through L1 all by itself, and the other one is the difference in the currents, I1 and I2 flowing through L2. So that's why we get these two terms. So now writing the mesh around mesh 1, V1 of t is equal to R1 I1 conventionally, plus L1 di1 dt conventionally, plus m d by dt of I2 minus I1, which is the mutual coupling term. But there's also a voltage induced without the mutual coupling term because of the presence of L2, and that would be L2 d by dt of I1 minus I2. But there's also another coupling term, which is minus m di1 dt. Continuing the example, for mesh 2, we want to go around the secondary mesh. We would get R2 I2 plus L2 d by dt of the current flowing through that inductor L2, which would be I2 minus I1, plus the mutual coupling from the first mesh, which is m di1 dt. It's the mutual coupling term that makes the network different than we would have for conventional networks. Let's look at another dot convention, if you will, description. V1 is equal to L1 di1 dt plus m di2 dt. V2 is equal to m di1 dt plus L2 di2 dt, which is what we have seen before. If we change the dot notation, as we found, we get an opposite set of equations. That's because the current I1 is now negative, producing a negative voltage for V1. The graphic is a little screwed up. Or minus V1 is equal to minus L1 di1 dt plus m di2 dt, and V2 is minus m in this case, di1 dt plus L2 di2 dt. Changing the dots in sort of opposite form, we get a similar set of equations with minus I2 current flowing and a resulting inversion of V2. So we get V1 is equal to L1 di1 dt minus m di2 dt as a result. That's where the minus m term comes in. And now minus V2 is m di1 dt minus L2 di2 dt. These three cases are the typical coupled coils, also known as transformers, and indicate the possibilities that we would have for the dot notation, the coupling. In the case of the third panel, that's equivalent to a negative mutual inductance, but as we said, that's really just an effect of the current directions and the dot notation. So let's write some equations now for V1 and V2, which I think we're getting quite proficient at, but look at the sign conventions. For V1, negative terminal at the top with the current I2 in standard form flowing out of the positive terminal and around the loop. And likewise for V2 with current flowing out, if you will, into the positive terminal of V2. So we have to be careful of the sign convention if we want to write valid equations according to the way the schematic is shown. So the first thing we'll do is convert it to the basic case. We'll let the current assumed to flow into where the dot terminal would have been, producing a positive voltage, and the other current I2 flowing into where the dot terminal would have been. Therefore, we would get minus V1 minus L1 di2 di1 dt minus m di2 dt. It's not shown in the graphic, but it is minus L1 di1 dt, of course. And V2 is minus m di1 dt minus L2 di2 dt. We can recast the equations algebraically and just write V1 is equal to L1 di1 dt plus m di2 dt, and V2 is minus m di1 dt minus L2 di2 dt, if you will. We can also recast this as in phasor form, which we're somewhat familiar with, removing the time-varying descriptions. So we have our equations for voltages V1 of t and V2 of t in terms of the inductance L1 and the mutual inductance M and the inductance L2. We can assume complex exponential sources. In other words, what we're actually saying is sinusoidal response, and write it as a phasor model now, which is much more convenient because we've been studying phasor models up to this point for circuit response. So that for the phasor now, instead of V1 of t, we have V of t equals j omega L1 di1 plus j omega m I2, and V2 is equal to j omega m I1 plus j omega L2 I2. And of course the j omega terms come about because we're taking the derivatives of the currents, and the currents are in fact sinusoidal. And we know from phasor models that those derivatives would become j omega as a result. So two coupled inductors can be connected in 4 different ways. Let's determine what the model might be for each case. So for example, I could link the inductors in this manner, and in the laboratory we could have an inductor JL1 and another inductor JL2 in close proximity with mutual inductance M, and we have the terminals available which we can then just wire. So in this case we wired a voltage source through the model entering at 1 with current capital I, phasor, and then we've shorted the terminals 2 and 3 together and then connected the negative terminal of the voltage source back to terminal 4. The currents in this case are flowing into the dots, if you will. We have the same current though, capital I, which obviously flows through the entire network. Therefore the induced voltage across the inductor due to the current I would be, as shown, plus or minus V1 and plus or minus V2. And by definition, from Kirchhoff's voltage law, V1 plus V2 is equal to the overall excitation voltage as a phasor, V. Substitution of our phasor relationships for the circuit is V1 equals j omega L1 I1 plus j omega M I1. I'm sorry, not I1, but I. There's only one current. And V2 is j omega Mi plus j omega L2I, if you will. There's only one current, capital I. Rearranging the two equations, we can also write it as capital V, since it's the sum of V1 plus V2 from network consideration, Kirchhoff's voltage law. And factoring out the j omega term, we would get j omega times the quantity L1 plus L2 plus 2M. Interestingly, that it's twice the mutual inductance, equals j omega L equivalent, if you will, which is L1 plus L2 plus 2M times I. For another case, let's wire the two coupled coils in this direction. We still have the common current I flowing through the coil, and the current still enters the dots. We have now, though, currents I and minus I because of the reverse nature of wiring the coils. Notice we've taken terminal 2 and putting it into terminal 4. The voltage is induced, V1 and V2 as before, but the currents are now different. Now we would then have, by Kirchhoff's voltage law in the wiring diagram, V is equal to V1 minus V2. Following the same analysis that we have in the first case, we could then produce an overall equation for V, which is j omega quantity L1 minus 2M plus L2 times I, and that represents the so-called L equivalent. That would be just without the j omega term. It would be L1 minus 2M plus L2 is the equivalent inductance. But you have to be careful because of the negative sign. We would certainly want L equivalent to be greater than or equal to 0. And in fact, it's not possible that the term could be negative. Therefore, there's a physical constraint on the possible values of the mutual inductance, M. For the third case, we have the same voltage source V deriving a current I, but I branches into two components, I1 and I2, and flows independently through the two coupled coils and then back to the source V. The currents are into the dots, I1 and I2. They're not capital I all by themselves anymore, producing a voltage plus and minus V. Notice that there's only one voltage because they're both in parallel across the source, capital V. And in this case, rather than getting a summation of voltages from Kirchhoff's voltage law, we know from Kirchhoff's current law that capital I must equal I1 plus I2 in phasor form. Therefore, V is equal to j omega L1 I1 plus j omega M I2. We now have two currents. Or V is equal to j omega M I1 plus j omega L2 I2. From the first restriction, we would also get I2 is equal to I minus I1. We can make a substitution to that effect, eliminating I2. Rearranging the equation then, for voltage, we get these voltage equations. The last one being V is equal to minus j omega quantity L2 minus M I1 plus j omega L2I. But V is also equal to j omega L1 minus M times I1 plus j omega Mi, sets of equations. We can normalize them by multiplying through and straightening out the representations. We would then get two equations and two unknowns, basically producing one equation. And that equation would be L1 plus L2 minus 2M times V. Again, two quantities equal to each other can be normalized together, is equal to j omega quantity M, quantity L2 minus M, plus L2 quantity L1 minus M, all times I. Dividing through, we would get V is equal to j omega. The numerator term becomes L1, L2 minus M squared, divided by L1 plus L2 minus 2M times I. For the fourth and last case, we have a different wiring consideration here. Slightly different. You'll notice that in the third case, terminal 3 was connected to the positive terminal of V, and in this case, terminal 4 is connected to the positive terminal of V. Currents into the dots. produce I1 and minus I2 as a result. Before it was I1 and I2. The voltage is plus V, but also plus or minus V, if you will, because of the direction of the current. We have then a coupled network that can be redrawn graphically that looks like this, with resulting currents I1 and I2. I is equal to I1 plus I2. Sum of the currents equals the input current I. And the voltage equation becomes V is equal to j omega L1 I1 minus j omega M I2, or minus V is equal to j omega M I1 minus j omega L2 I2. Two representations because of the two parallel networks with mutual coupling. We can straighten out those two equations and write that in the same kind of substitution that we did for case 3. You should try this yourself algebraically and produce a result which is V is equal to L1 L2 minus M squared over L1 plus L2 plus 2M times I. Unfortunately, in that equation, what is missing is a term j omega. There should be a term j omega out front. Let's find the voltage V0 in this coupled network. We have a voltage source of 24 angle 30 degrees flowing with a current I1 through a 2 ohm resistor, and then a inductor whose reactance is J4. It is mutually coupled to a second coil whose reactance is J6, but notice the mutual coupling also has the same J notation for reactance. It's J2, and J2 is essentially M. And in the secondary circuit, we have a current I2, which results from the mutual coupling through a capacitor whose reactance is minus J2, and a resistor of 2 ohms whose voltage across it produces V0. So we do have the coupling here, which is certainly different than the types of networks that we have been studying up till now. The coupled inductors themselves define their voltages and currents by definition and the dot notation with the directions of currents I1 and I2. So the voltage across the first coil, if you will, would be plus or minus V, for example, because of the dot notation. And the voltage across the second coil would also be plus or minus V, again, because of the dot notation. Notice where the positive signs are. The secondary current, though, is minus I2. That's because of the dot notation. That means that it would develop a current of minus I2. Currents flow in. And in this case, we have a current I1, which is flowing in at the dot. It's minus I2 because we had defined the mesh current I2 as being a clockwise current in order to produce the voltage V0. So we have to be very careful about polarity. So write the loop equation now in terms of the coupled inductor voltages. By Kirchhoff's voltage law, 24 angle 30 degrees is equal to 2I1 plus V1. That seems easy enough. By Kirchhoff's voltage law also, minus V2 minus J2 I2 plus 2I2 is equal to 0. There is no representation of any other independent source in the secondary equation, so that's why we get equal to 0. Write the equations now for the coupled inductors. For the mutual inductance circuit, we would get V1 is equal to J4I1 plus J2 minus I2. J2 is the mutual inductance, of course, and it's minus I2 because of the current flow. And V2 would be J2I1 plus J6 minus I2. By definition, V0 would be the resistance of 2 ohms multiplied by I2. Replace the loop equations and essentially do the algebra as a result. Replace V1, if you will. Replace V2, if you will. Do the algebra, and we get V sub S is equal to the quantity 2 plus J4 times I1 minus J2 I2. And from the second equation, 0 is equal to minus J2I1 plus quantity 2 minus J2 plus J6I2. Normalize them so that we can manipulate them. We will get J2V sub S is equal to quantity 4 plus quantity 2 plus J4 squared times I2. Or if you will, I2 is equal to J2VS minus 8 plus J6. We can normalize it by multiplying top and bottom by minus J. And we'll get 2VS over 16 plus 8J. Or V0 is equal to 2I2. So that's basically VS divided by 4 plus 2J. Please note that in the graphic, it's shown as minus I2 because that would be the representation that we would get. Unfortunately, or fortunately, because of the mutual inductance, we get the circulating current in green as a result, producing V0 because of the dot notation. Substitution of the numbers and producing an algebraic answer, we get 5.37 volts and an angle of 3.42 degrees. Here we want to write the mesh equations for this coupled network. In this case, the two coupled coils are separated by a resistance R2, and we do have the dot notation. Let's define the variables for the coupled coils. The voltage V1 across the first coupled coil in the direction shown with the dots. Likewise, the voltage V2 for the second coil with the direction shown by the dots. The current that flows through the first leg down through the first coupled coil is I1 minus I2. We get that from conventional mesh current definitions. We have clockwise flowing currents, and down through that particular path, it would be I1 minus I2 as phasors. Likewise, for the second coil, it's I2 minus I3, looking at the conventional direction of the mesh currents. Let's write the loop equations now in terms of the coupled inductor voltages. So the source V is equal to R1I1 conventionally, plus V1 for now, plus I1 minus I2 divided by j omega c. And of course, j omega c is the 1 over j omega c is the reactance of the capacitor. And the current flowing through it is I1 minus I2. Also then, we can take the equation and rewrite it, recast it as minus V1 plus R2 now for the middle mesh, I2 plus V2 plus R3, I2 minus I3, because I2 minus I3 is the current flowing through R3, plus, again, the current I2 minus I1 divided by j omega C1, if you will. And because we're going around a mesh without any independent sources, it's equal to 0. And since we have three meshes, we have three equations. So the third mesh is minus V2 plus I3 divided by j omega C2 plus R4 I3 plus R3 I3 minus I2 equals 0. Now, we haven't done the coupling. We haven't done the coupled inductors, but these are perfectly correct representations for the network in terms of the mesh currents and induced voltages. And we have these terms V1 and V2 that are due to the coupling, so we now want to eliminate them. V1 and V2 are not considered as independent sources the way the source capital V would be. So what would V1 be? Well, V1 would be j omega L1 times the current that flows through it, which is I1 minus I2. But because of the coupling and the dot notation lining up with the direction assumed for V1, we will get plus j omega M quantity I2 minus I3. I2 minus I3, of course, being the current that flows through the second inductor producing the coupling, I2 minus I3. Likewise, V2 would be j omega M I1 minus I2 plus j omega L2 I2 minus I3. Notice the coupling terms. In the first equation, it was j omega M but times I2 minus I3. And in the second equation, it's still j omega m, but it's the current I1 minus I2. Replace these particular definitions for the coupled inductors into our loop equations and essentially rearrange the terms algebraically. So we'll get V is equal to the quantity of R1 plus j omega L1 plus 1 over j omega C1 times I1 minus j omega L1 minus j omega M plus 1 over j omega C1 times I2 minus j omega M I3. This little algebraic manipulation I think you would want to do to make sure that you have the technique. It's important to substitute correctly and rearrange the terms. For the second equation, we'll get 0 is equal to, and I'm not going to bother reading it because it's quite complicated. Again, you should try to do that to get the terms and the terms correctly, including the polarity and the signs. And then last, there's another equation equal to 0. It comes from the third equation in our mesh. And again, I'm not going to read it, but again, please do it because I think it's important algebraically to get it correct. All we've done is take the equations in 2, the loop equations, and substituted the equations from 3 for the coupled inductors and have performed the rearrangement, producing 3 new equations, if you will. And in these cases, we have removed V1 and V2 and replaced it with the coupling indicated by capital M, the mutual inductance. All right, so let's see if we can move on to a learning extension where we want to find I1, I2, and V0 as phasors in this particular network. We have 24 angle 0 again in the first mesh producing a current I1. Let's be very careful about polarities and assume directions. We're taking our common way of assuming mesh currents as clockwise. And the first mesh has 4 ohms and an inductor of J4 reactance, mutually coupled with the dot notation whose mutual coupling M is J1, to a second mesh whose inductance reactance is J8. Notice the dot notation in series with a 2 ohm resistor and also a minus J4 reactance capacitor whose voltage across it represents V0. So by definition, again, we go by the definition of how we've drawn the mesh currents conventionally as clockwise. V0 is equal to minus J4 I2. Define the variables for the coupled inductors. Since we have dot notation, which was different than the previous learning extension, notice that V1 is plus minus, the plus lining up with the dot, and V2, if you will, is minus plus, or if you will, the plus lines up with the dot. And we have circulating currents that have to be taken into account, shown by the blue arrows. The currents enter where the dots are, in the first mesh in the direction of I1, and in the second mesh in the circulating direction of I2. Write the loop equations now. V sub s is our source. V sub s plus V1 plus 4I1. Notice we've written it as V1 without worrying about the mutual term at this point. Equals 0. That's a loop equation. And V2 plus quantity 2 minus J4 times I2 is identically equals 0. That's the second mesh. Do the coupled inductors equations. V1 is equal to J4I1 plus JI2. And V2 is equal to JI1 plus J8I2. Replace and rearrange the loop equations by the coupled inductor equations. Quantity 4 plus J4 times I1 plus JI2 is equal to minus V sub s, conveniently. And JI1 plus quantity 2 plus J4I2 is equal to 0 from the second equation. Normalize and remove terms and rearrange. We get quantity 1 plus 8 times quantity 1 plus j times quantity 1 plus 2j. The whole quantity is multiplied by I2 equals jVs. Again, manipulations should be done to make sure that you have the technique and can solve these types of linear equations. Voltage is in volts, impedance in ohms, and currents are in what? Well, currents are in amperes, of course. So I2 is equal to JVS divided by minus 7 plus 24J, which is what we get from the last equation by substitution and algebraic manipulation. We can normalize that, and we can end up as 24 angle 0 over 24 plus 7J. Still can't quite divide it because we have as we found in previous chapters, we have a polar form in the numerator and a rectangular form in the denominator. So we'll recast it as 24 angle 0 divided by 25 angle 16.26, or I2 is 0.96 angle minus 16.26 amperes. Also, JI1 plus quantity 2 plus J4I2 is equal to 0. We could normalize that and solve. And we end up with I1 is equal to J quantity 2 plus J4 times I2. We've already solved for I2. And therefore I1, after manipulation, of course we have the product of two polar representations, so we're okay. We can perform that manipulation because we have everything normalized as polar forms. We get I1 is equal to 4.29 angle 137.17 degrees in amperes. V0 we also wanted to find, but we do know what I2 is, so V0 is minus J4I2, and manipulation of the polar representation. Notice that minus J is 1 angle minus 90, and therefore V0 is 3.84 angle minus 106.26 volts. Another learning extension, write the Kirchhoff's voltage law equations. All right, we have two meshes producing circuiting currents I1 and I2 with a voltage source V1. We have J omega L1, J omega L2, and resistive loads of R1, R2, and R3. Define the variables for the coupled inductors. All right, well, since we have circulating current I1, it flows in at the dot, produces the voltage plus and minus VA across J omega L1 according to the dot notation. And we also have circulating current minus I2. Notice that the mesh current was assumed to be clockwise, but we want the current to enter the dot to produce a voltage minus plus VB. Remember, the dot notation indicates where the positive voltage is. And in order for that to happen, we would need minus I2 to flow in at that location. Write the loop equations now in terms of the inductor voltages. VA plus R2, and of course the current that flows down through that particular resistor R2 is I1 minus I2, plus V1, which is the voltage source, plus R1 I1 equals 0. That's the first mesh. I'm sorry, the first loop. And minus VB plus R3 I2 minus V1 plus R2 times I2 minus I1 equals 0 is the equation for the second loop, Kirchhoff's voltage law. Voltages around the loops equals 0. Write the equations for the coupled inductors, being careful of the polarities. We would get VA is equal to J omega L1 I1, because I1 is flowing in the proper direction, plus J omega M, but it's minus I2, because of the assumed direction of the current I2. Likewise, VB is J omega M I1 plus J omega L2 minus I2. Replace into loop equations and rearrange. Quantity R1 plus R2 plus J omega L1 times I1 minus quantity R2 plus J omega M times I2 is equal to minus V1. Second equation, minus quantity R2 plus J omega M I1 plus quantity R2 plus R3 plus J omega L2 times I2 is equal to V1. In this learning example of coupled coils with mutual inductance, we want to determine the impedance as seen by the source being V sub S. So we look at the first circuit and we notice that V sub S has a series impedance, which is given as 3 plus J1. It's not in any component form, but it is known to be 3 plus J1. And the load impedance is known to be 1 minus J1. Again, not given as any components, but that's what it's given as. We also have J omega L1 is equal to J2, so we know that omega L1 is 2, if you will. And J omega L2 is equal to J2, so we know omega L2 is equal to J2. And J omega M we're given as J1, so omega M is equal to 1. Again, you may be given L and M, L1 and L2 and M and omega separately, but you would then substitute them and calculate omega L1, omega L2, and omega M, if you will. The source impedance that we want to calculate is actually what the source sees, so that's V sub S divided by I1 as phasors, and we'll call it Zi. Let's write the variables for the coupled inductors. I1 is in the mesh current direction as indicated, and I1 does flow into the dot, so that's good. I2, unfortunately, is clockwise, so we have to consider I2 as being minus I2 as far as the dot notation is concerned in this particular case. Write the loop equations now in terms of coupled inductor voltages. ZSI1 plus V1, we'll just leave it as V1 for now, which is a way we've been solving these equations, equals VS. And minus V2 plus ZLI2 is equal to 0. Again, we'll leave it just as V2 for now. Now write the equations for the coupled inductors so that we can replace V1 and V2. We get V1 is equal to J omega L1 I1 plus J omega M, but it's minus I2. Likewise, V2 is J omega M I1 plus J omega L2, but it's minus I2. Replace and do the algebra, sometimes not insignificant. This case might be relatively straightforward. Quantity Z sub S plus J omega L1 times I1 minus J omega M times I2 is equal to V sub S minus J omega M I1 plus quantity Z sub L plus J omega L2 I2 is equal to 0. Straighten out as we tend to do and bring the two equations together. Again, a step that you should do. Sometimes that seems to be one of the hardest parts to do. We then get a long and complicated equation, which I'm not going to read to you, but hopefully you would want to do that to make sure you get the same equation. Finally, we take the ratio of V sub S divided by I1. We do have an equation for V sub S and I1 by normalizing right above us. So we just form the ratio, if you will, V sub S over I1 algebraically. And we get Z sub S plus J omega L1 minus quantity J omega M squared over ZL plus J omega L2. Again, you should verify these algebraic manipulations yourself to make sure that you have the technique. Substitution in the values, because we did everything in terms of unknowns. Substitution in the value, we get 3 plus J3 minus quantity J1 squared over 1 plus J1. And of course, that's the same as 3 plus J3 plus 1, because J1 squared is actually minus 1, and then we have a minus sign out front, so we get plus 1 over 1 plus J. We can normalize the whole Zi, if you will, and produce something in a little bit more reasonable form of 3.5 ohms real plus J 2.5 ohms reactive. Zi is 4.3, then angle 35.54 degrees. But this is not a phasor. Remember that when we first considered impedances, these are a polar representation of an impedance, which is not a phasor. Phasors are due to currents and voltages. This is a derived effect, the impedance. Another problem on determining the impedance is seen by the source. Well, we have a V sub S source at 120 angle 0, a 2 ohm resistor, a minus J1 capacitive reactance, a J2 coupled inductor whose mutual coupling is J1, and another secondary side whose coupled inductor is J2. Notice the dot notation again with a 2 ohm resistor, a minus J2 capacitor, and a J1 inductor. That last inductor is not part of the coupling. There are no dots there. All right. Well, Z sub S could be taken as 2 minus J1. We can just take that as being the source impedance, if you will. And what we're interested in is the load impedance on the other side. That would be 2 plus minus J2 in parallel with J1. And again, we've taken that network because there is no coupling. So we have a Z sub S and a Z sub L as we've had before, with a coupled coil system between them. So ZL then can be written as 2 plus 2 over minus J, or 2 plus 2J, product over the sum rule for the parallel. We can write the variables for the coupled inductors. What we'll choose to do is write I1 again, and we'll write I2 as flowing through the second coupled coil, and also Z sub L as an entity, because we've now put those three components as one component whose value Z sub L is 2 plus 2J. We'll write the loop equations then. V1 plus ZS I1. ZS is a convenient placeholder, is equal to V sub S. And V1 is in the right direction. Notice the dots. And V2 plus ZL I2 is equal to 0. And again, V2 is in the right direction because the dot, but because the circulating current I2 that we've assumed also enters the dot. Write the equations for the coupled inductors. V1 is equal to j omega L1 I1 plus j omega M I2. And V2 is j omega M I1 plus j omega L2 I2 in this particular coupling situation. Replace and do the algebra. And we have some limitations because we can substitute in Z sub S and ZL. One can choose directions for the current. If I2 is reversed, one gets the same equations as in the previous example. The solution for I1 must be the same as the expression for the impedance must be the same. So hopefully we get the same representations if we're careful. And we can then substitute in the values and manipulate them algebraically, and producing a result of 2.1 plus 0.8 J ohms, if you will. Or Z sub I is equal to 2.25 angle 20.85 degrees. This is section 2, energy analysis. Here we would like to determine the total energy stored in a coupled network. We have considered energy in steady-state AC before in previous chapters, and we determined that that was the integral of the power over time, and that's the analysis that we're going to use here. This development is different from the one in the book, but the final results are supposedly the same, and we should compare and contrast the development in the book to verify that. The equations for the coupled inductors, V1 is equal to L1 di1 dt plus or minus M di2 dt. V2 is plus or minus M di1 dt plus L2 di2 dt. And of course it's plus or minus M depending upon the dot notation from the direction of the coupled coils. The total power supplied to the network in this coupled network is P of T, P sub T of T, is equal to V1 of T times Vi1 of T plus V2 of T in the secondary coupled side plus I2 times I2 of T. Straightening out the equations and writing one coupled equation for the total power, we end up with P sub T of T is L1 I1 di1 dt plus Mi1 di2 dt plus or minus M di1 dt times I2 of T plus L2 I2 di2 dt. Now from the chain rule from calculus, I2 times di2 dt is 1/2 di2 squared. Likewise, the first term becomes 1/2 the I1 squared, and our two coupled equations become m the I1 the I2 dt, if you will. So the total power can be then rewritten as the time differential d by dt of the quantity 1/2 L1 times I1 squared plus or minus m I1 I2 plus 1/2 L2 I2 squared. We're going to integrate that over time in order to produce energy from minus infinity to current time t. And we'll call that W of t as a result for the energy. 1/2 L1 I1 squared plus or minus m I1 I2 plus 1/2 L2 I2 squared. We can do an algebraic manipulation in order to make the equation slightly more understandable. This term here that you see just added, 1/2 m squared over L2 times I1 squared minus 1/2 m squared over L2 times I1 squared, that's identically adding 0. And we're doing that so we can group terms together. So we've added 0 to the W of t equation. It should not change the equation, but it will allow us to group terms. Algebraically then, when we group terms, we'll end up with W of t equals 1/2 L1 minus m squared over L2 times I1 squared plus 1/2. Notice that the quantity is squared though. Quantity L2 I2 plus or minus m over the square root of L2 times I1. But the whole quantity, of course, is squared. So we know Wt, the energy, is being consumed, and we know it must be greater than or equal to 0, and therefore the term which has the negative in it, L1 minus m squared over L2, must be greater than 0 as a result. That means there is a constraint on m. M must be less than or equal to the square root of L1, L2. That's an energy constraint, but it's a practical constraint in that sense too, that the mutual coupling, capital M, must be less than the square root of L1, L2. We'll call that particular analysis, if you will, the coefficient of coupling, K. K is equal to M divided by the square root of L1, L2, the coefficient of coupling, given the notation K. In this learning example, we want to compute the energy stored in the mutually coupled inductors. We're going to assume steady state operation. We're given a 24-volt source at 24 cosine 377t, a 2-ohm resistor, an L1 inductor has mutual coupling M, and an L2 inductor with a resistive load of 4 ohms. We're told that L1 is 2.653 millihenries and L2 is 10.61 millihenries, and that K equals 1, and we're interested in the response at time equals 5 milliseconds. Of course, we have the equation that we just developed for the energy, 1/2 L1 I1 squared plus m I1 I2 plus 1/2 L2 I2 squared. But we must compute, obviously, m I1 and I2 in order to find what the energy might be. Well, m is equal to k square root of L1 L2. Substitution k equals 1 in the values of L1 and L2. We can then get m is equal to 5.31 millihenries. We are going to use frequency domain analysis or phasor analysis. We know that omega is equal to 377, and therefore omega L1 is 1 ohm, omega L2 is 4 ohms, and omega M is 2 ohms. We can recast the networks then now with their reactances as shown here. This is the circuit in the frequency domain. Notice that I1 of t is now the phasor I1, and I2 of t is now the phasor I2, and 24 cosine 377t, omega is removed, and we now write it as a phasor as 24 angle 0 degrees. Circulating currents capital I1 and I2 in phasors, and directions of currents, which are dictated by the dots, not necessarily the mesh currents, but by the dots. So we see that the direction of I1 agrees with the dot, and the direction of the dot in the secondary network produces minus I2 as far as the inductor is concerned, in order to produce a voltage across the inductor as shown with the polarity. Notice that the positive signs line up with the dots. Merge the writing of the loop and coupled equations in one step. If you don't want to do this, you can perform the analysis the way we've done up till now. You should do that and to get the same answer, but if you'd like, you can write 2I1 plus JI1 minus J2I2 is equal to 24 angle 0, and also 4I2 minus quantity J2I1 minus J4I2, quantity closed, equals 0. We can solve then two equations and two unknowns to get I1 and I2 by elimination or other methods. We get I1 is 9.41 angle minus 11.31 degrees amperes, and I2 is 3.33 angle 33.69 degrees amperes. We now need to convert back to the time domain because that's what we're looking for, and our time domain solution therefore is 9.41 cosine 377, because that's omega t minus 11.31 degrees, and I2 is 3.33 cosine omega t 3.717 plus 33.69 degrees. The term obviously 377t is in radians. That's our definition of omega t for the argument of the cosine. At t equals 5 seconds, we can substitute in what t is equal to. 5 milliseconds. We can substitute 5 milliseconds for t times 377, and we get 1.885 radians, which is, on your calculator, the same as 108 degrees. So remember that 377t is in radians. Substituting time in seconds produces radians as a result. I can convert those radians to degrees. And therefore, substitution of 108 degrees with the phase angles as indicated, we get I1 at 5 milliseconds is minus 1.1 amperes, and I2 at 5 milliseconds is minus 2.61 amperes. And therefore, we can then calculate W, which represents the energy at 5 milliseconds. We get, by the formula that we've used in prior learning assessment, 0.5 or 1/2 times 2.653 times 10 to the minus 3 times minus 1.1 squared. Of course, 2.653 is our representation of our L1, plus 5.31 times 10 to the minus 3, which is our representation of M, times minus 1.1 times minus 2.61, and the last term 1/2 or 0.5 times 101.61 times 10 to the minus 3, which is our representation of L2 in millihenries, times minus 2.61 squared, and the overall units are in joules, or capital J, joules. Performing the calculation, we get that the energy stored in the mutually coupled inductors at 5 milliseconds is 22.5 millijoules. Another problem, determine the energy stored at t equals 10 milliseconds. Voltage source of 12 angle 30 degrees, a 2 ohm resistor, a mesh current of I1 already in phasor form. We're told that F equals 60 hertz. We need to know that for the time varying solution. That of course is not omega, but that's 2 pi F would be omega. We have a J2 coupled coils by J1 with a secondary circuit with J2 and minus J2 with a 2 ohm resistor and circulating current I2. The time varying equation for W of t we have seen. We know that the currents have to flow into the dots in order to provide the voltage drops as shown. Notice the plus sign where the dot is. So the current must flow into the dot on the left-hand network and into the lower dot onto the right-hand network. Therefore, 2I1 plus quantity J2I1 plus J1I2 equals 12 angle 30 degrees in the first mesh. And in the second mesh, J1I1 plus J2I2 quantity plus quantity 2 minus J2 times I2 is equal to 0 in the second mesh. We would then be able to organize the two equations algebraically. We can just bring terms together. We get quantity 2 plus j2 times I1 plus j times I2 equals 12 angle 30 degrees. And from the second equation, we get j I1 plus 2 I2 equals 0. Therefore, we have two equations and two unknowns, and we can solve. We can make substitutions, if we will, from first and second equations. From the second equation, we get I2 is equal to minus 0.5 j I1, and we can substitute that back. And algebraically, we can solve then for I1 by elimination, and we get a value of 3.75 angle minus 8.66 degrees. Likewise, I2, by definition from equation 2, is minus 0.5 ji1, so therefore it's minus 0.5 j, which is 0.5 angle minus 90 times 3.75 angle minus 8.66, gives us 1.875 angle minus 98.66 degrees, all as phasors for I1 and I2. Let's go back to the time domain. Well, in order to do that, we have to have radians. This is a common mistake. If you're given 60 hertz, that is not the radian frequency. The radian frequency is 2 pi f, or 377. Therefore, omega L1 is 2. And we would get then a value for L1, which we can solve since we know what omega is. And likewise, a value for L2, since they have the same reactance. It's 0.0053, or if you will, 5.3 millihenries, thousandths of a henry. The mutual then, we know, because we know it's J1, so we know omega. In this case, we don't need to know the coupling factor, wasn't asked for. So verify that you could calculate that the mutual coupling M is 0.00265, or if you will, 2.65 millihenries. Now we can convert back to the time domain. I1 of t is the amplitude that we calculated, 3.75, cosine omega t, 377t, with the angle minus 8.66 degrees that we calculated. And I2 then would be the amplitude that we calculated, 1.875, again, cosine omega t, 377t, minus the angle we calculated, 98.866 degrees. At the particular time that we're asked to solve, namely 10 milliseconds, we can calculate 377 radians per second times 10 milliseconds. 10 milliseconds is 0.01, which is 3.77 radians, which is 216 degrees. Again, verify that on your calculation with a calculator. Therefore, I1 at the particular time, 10 milliseconds, is minus 3.33 amperes, and I2 at 10 milliseconds is minus 0.86 amperes. The power can then be calculated, as we've done before, in joules, substitution of the numbers that we just got at the particular time interval, 10 milliseconds, and we find out that the answer is about 30 millijoules for the energy stored at 10 milliseconds. With that, we have the end of Chapter 10, Magnetically Coupled Networks, Sections 1 to 2.